I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics: Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. This is the last lecture before the exam, and then tomorrow we'll go through review. I'll send you out a review lecture. Look through it to see what questions you have. And another thing that I do in both of your assignments is if you're phrasing it incorrectly or in an improper way, I'll cross out the improper way and enter in the proper way or whatever. So anytime there's my ink marks on your paper, it's for a reason, and it's to help coach you towards this is the more appropriate way to give a formal decision or to interpret. Like a lot of times I'll just say interpret, because all you did was give a value and you didn't interpret. And so if you're like, well gosh, how am I supposed to interpret it, or what do you mean by that? We can talk about that tomorrow so you can get more specifics on that. Simple linear regression, second lecture. And so yesterday we talked mainly just introducing the linear equations and the regression equation and learning how to predict values using your regression equations. So to remind you, simple linear regressions estimate the population model. And so a model is a mathematical equation, and this is the population model that we're trying to get as close to as possible. Like what's the true population model out there for the relationship between X and Y? Like with gender and exercising or whatever, there's a true relationship out there. Again, if we sampled the entire population, we could come up with this equation to find out what the actual relationship between gender and exercise levels are. But we don't have the resources to sample the whole population, and so what we do is we estimate it with a sample model. And so the sample model is identical to the population model, and the only added thing in the population model is this error term, which basically accounts for sort of error in our study. And there's multiple sources of error, sort of like how we talked at the beginning of the course about sampling biases and other types of bias that sort of just get into our study. And so this error term captures all of that. And the goal is to reduce the amount of error. So one way to reduce error is to increase your sample size and other things like that. But basically, what we do with our data is find the regression equation that best fits our data for the relationship between X and Y. So there's sort of an algorithm. An algorithm is a procedure or a process that you just sort of walk through when you're approaching a familiar situation. So similar, Chelsea's at the free throw line, she walks through a procedure. You guys have a bunch of data and you want to do a simple linear regression. There's a procedure that you walk through. And the first is just simply to plot the data. So that's when we've done like box plots or scatter plots or the histogram. So it's just visually what's going on with your data. And so in that way you can see if there's outliers, you can see if there's a linear relationship or just some things that are just easily observed visually. The second step is to fit the model. This is always done by computer, and so really, like on GSS, when you're plugging in your two variables, you're telling GSS to find the best fitting equation that shows the relationship between the two variables that you're looking at. It doesn't show you the equation, it just creates the equation and then computes the outcomes of that equation. But you're taking your data and you're finding the best fitting, in this situation, the best fitting line that cuts through your two variables. The third step is to check conditions, and there's a whole litany of different conditions that have to be satisfied. We're not going to necessarily go over those, but there are, in each of the things that we've looked at, there's specific conditions like sample size and that the data be normal and things like that that need to be met in order to make certain assumptions. After you've done that, what you want to do is test for significance. So, like I said, the computer will create a model or an equation for anything you put in there, and what you'll want to do is test for significance and see if the relationship that you're observing is a significant relationship. If it's not significant, a quick interpretation of that is that there is no relationship, that the relationship is zero. If there is no relationship between two variables, you can stop the process right there, because any type of difference you did observe is likely to have happened just by random chance. So that's why a key step is to test for significance. And once you've established that the relationship is significant, then you can use the model to make inferences, like from your sample to the whole population, or make predictions about future situations. So this is the procedure that we walk through, and I'm going to take an example today that walks us through each of these. The one that I won't go through is the checking conditions, because this is what we want to focus on. We're going to look at presidential approval and re-election. The question is, can we use Obama's approval rating to predict his margin of victory or defeat when he runs for re-election? Again, this is a scenario where we have some data and we're going to use the data to make a prediction about a future outcome. And so the data that we're using is data on all incumbent U.S. presidential candidates since 1940. And so there's been 11, I think technically 12, but one was dropped, 11 U.S. presidents who were sitting presidents and were running for re-election. And so then that's the data that we're looking at. And the dependent variable was in their election, in the bid for re-election, what was their margin of victory or defeat? So by how many percentage points did they win or lose their second election? The independent variable is approval rating. So, at the time of going up for re-election, they had a certain approval rating that was measured. And so for each of these incumbent presidents, we have both their approval rating and also the margin of victory for their re-election. That's the sample that we're going to use to then eventually predict Obama's bid for re-election. So in a sense, these past 11, we already know the outcome, and so we can see what the relationship might be. With Obama, we don't know the outcome, but we can give an estimate or a prediction of what we think it'll be based on past experiences of these previous 11 presidents. The first thing to do is to plot the data. The idea is to make observations about the data. And it can be any type of observation. Approval rating changes every day. It actually changes every minute, probably. And so I'm wondering if the approval rating, what I'm suspecting is that it's the approval rating on the day before the election, possibly. I don't know. Or it could be the average approval rating over the 3 months leading up. When I ask you guys about the variables that you're using, I'll ask, well, what is it really measuring? Because it makes a difference whether it's his average approval rating over his entire presidency or the day before the election, or, was it his lowest approval rating? We don't know. It's important to know your data that you're working with versus just saying, okay, I have these two variables and I'm going to start charging forward with fitting a model. So the first is to plot the data, kind of know your data, become familiar with it, see if there's any potential problems. And the question that you can ask, is the trend linear? Specifically for doing the analysis of simple linear regression, we want to know, is the trend linear? The next step is to fit the model. And this is where the computer will walk through all different possible lines that can go through these data and find the best fitting line. And when it fits the line, it comes up with this equation as the margin of victory equals negative 36.5 plus 0.84 times approval rating. So that's our regression equation. We're going to assume that it meets all the conditions, and we're going to move on to testing for significance. And sort of like what we looked at yesterday was there's two ways to test for significance. One is via confidence intervals, and the other is through hypothesis testing. So clearly these are two things that you need to just know down pat: how to calculate confidence intervals and how to conduct hypothesis tests. Because we've done that with almost every example. In some form or another, we've looked at confidence intervals and hypothesis tests. So this is a common output that you'll get. Hopefully you've noticed that it's somewhat similar to what the GSS puts out. I think GSS calls this the constant, and so that's another name for intercept. And then whatever variable that is your independent variable, it's going to put right here. This is sort of information about the coefficients, and that's the beta naught and beta 1. And this column right here, where it's estimate, is estimating the value for beta naught and beta 1. So then what we want to do is to know if this beta 1 is significant or not. Is it significantly different from 0? And so in a sense, what we have here is a point estimate for beta 1. So we want to calculate the 95% confidence interval for the slope coefficient. And this is called the slope coefficient because it determines the slope of the line in the regression. Our familiar formula for confidence interval, this is the general formula, and then we kind of need to identify what's our sample statistic. We need to look up the t-star and make sure that we're using the right standard error value. Specifically for regression equations, our sample statistic is beta 1, and then we use the standard error of beta 1, and then t-star is what we look up on StatKey. As you're creating your cheat sheet, make sure for each type of scenario we've confronted that you put down how to calculate the degrees of freedom, because it's different when you're doing a test for single variable means versus a difference in means versus correlation versus doing regression equations. So as you're creating your thing, don't forget to include degrees of freedom. Then if you plug in all of those values, we come out with a 95% confidence interval of 0.48 to 1.2. What can we conclude about this confidence interval? We're testing for significance. We want to see if this value of beta is significantly different from 0. Just in general, what a confidence interval tells you is the range of plausible values for your estimate. So like beta 1 is a point estimate, just like a sample proportion or a sample mean. And what the confidence interval says, okay, that point estimate is going to vary from sample to sample, and so what's the range of plausible values for that point estimate? And a lot of times we want to see if that point estimate is significantly different from 0. Because if the confidence interval includes the value of 0, like let's say negative 0.48 to 1.2, then you would say, well, one of the plausible values for this point estimate is 0, so it's not significantly different from 0. Because we could have easily observed a value of 0 for this relationship, which would have basically said approval doesn't have a significant effect on presidential outcomes. So because the confidence interval doesn't include 0, then we can conclude that it's significantly different than 0. This is my question, and probably a question for you all, is so we say, it's significantly different from 0. What does the it refer to? What did we just discover? It's the slope. It describes for every unit increase in approval rating, the predicted margin of victory will increase by a certain amount. And in this case, it'll increase by 0.836. It's the same idea of correlation, but when we're using regression equation, it quantifies what the relationship is. So for every unit increase in your independent variable, will lead to a 1-unit increase in your dependent variable. It's the relationship between approval rating and margin of victory. And I think if you're interested, in the last lecture, one of the extra slides at the end shows how what you're finding here is very similar to correlation, and so it's very closely related, but by calculating a regression equation, we can actually quantify if the approval rating increases by 10 percentage points, then we know the margin of victory is going to increase by 8.36 percentage points. It just gives you a clear way to quantify how it would change across units. So then the second way to test for significance is through hypothesis tests. And so we use sample statistics calculated by the software program to conduct hypothesis tests to see if the slope coefficient, i.e. the association between approval rating and the margin of victory, is significantly different from 0. So again, this is the same output. If we are going to do a hypothesis test, what is the null hypothesis for this hypothesis test? Beta 1 is 0. And the reason why beta 1 is 0, well, again, null hypothesis is a hypothesis under conditions where there is no effect, there is no relationship. And so if beta 1 equals 0, that basically means there's no relationship between approval rating and margin of victory. And so we want to know, is approval rating the effect or relationship that it has on margin of victory, is it significantly different from 0? And so that's why our null hypothesis is saying it's 0, there's no effect. And then our alternative hypothesis would be beta 1 doesn't equal 0. So for regression equations, that's how we set up our hypothesis test. And what type of tail test would this be? Two-tail. Why two-tail?
Because we set our alternative hypothesis to not equal 0, so if it's less than 0, it's still be.
Okay, yeah. So we just want to know if it's different from 0. We don't care if it has a positive relationship or a negative relationship. We just are interested in what are the chances that it's going to be significantly different from 0, either on the positive side or on the negative side. So here's our null hypothesis and alternative, and I called it beta A so that we'd know its approval. So really all these little sub things are to be of assistance. So the more intuitive you make them, the better it is for yourself and the better it is for me, because then I know what you're actually calculating. So then it's the same formula that we use where you have sample statistic minus the null value, and so it's whatever the null value of beta hat is there over standard error, and it's the standard error of beta hat A. The null value for beta is 0, and so then what we have here is 0.8356 over 0.1631, just walking through the equation, and we come out with a t equals 5.12. We want to calculate the p-value for this test statistic. What type of distribution does this test statistic form? So when we go to StatKey, we click on t, but the reason why we do that isn't just because it's the same letter as up here, but it's basically saying that the distribution of those values will follow a t distribution. All the possible test statistics when the null is true follows a certain distribution. And so then we want to say, okay, well, if it follows this certain distribution, where does our value that we got from our sample fit on that distribution? And if it sort of fits right in the center, then we're like, gosh, we could have easily gotten that value if the null hypothesis was true. But if it fits way out on the end, then we say there's a very, very small probability that we would get this outcome, get a value as large as 5.12 if the null hypothesis was true. So I won't belabor it and go to StatKey. I'll just say, well, actually with this one I will, because I think the two-tail is a little bit confusing and it can trip you up. So degrees of freedom are 9. We're doing a two-tail test and our test statistic is 5.12. Okay, how do we obtain our p-value? If we're doing a two-tail test, we want to know the proportion of values that are as extreme as our test statistic. It could be very plausible that you guys would sort of look at this and be like, okay, this is how we do it. Our p-value is 0.003. But when you're doing a two-tail test, you need to calculate the proportion of values in the left tail and the proportion of values in the right tail. And in a quick shorthand for that is just multiply this value by 2. So just sort of in your mind, remember, if I'm doing a two-tail test, make sure I'm calculating the probabilities for both tails. A lot of times we just do a one tail, or whether the p-value is 0.0003 or 0.0006, they're both highly significant, so a lot of times they notate the p-value as 0, and so you don't even see that, did they do a right tail or a two tail? And it's important to know what they did, but the conclusion will be the same, that it's highly significant. So a lot of times people kind of just breeze through it, and you're not even picking up on it because you're like, well, I don't know, it's 0. I'm not sure if it's technically 0.0003 or 0.006. But the key is your alternative hypothesis determines if it's a right tail, left tail, or two tail. The interpretation or the conclusion would be that the data provides strong evidence that the slope for approval rating is significantly different from 0, specifically that there is a significant association between approval rating and the margin of victory. So what we've done with the confidence interval and the hypothesis test is just establish whether or not approval is significantly related to margin of victory. And the hypothesis test is a superior test, mainly because with the confidence interval, we just know that it doesn't include the value of 0, but with the hypothesis test, we see that the probability of seeing a relationship as extreme as what we see in our sample, the probability of seeing that, if the null hypothesis was true, is 0.006. So we have a high degree of confidence that there is a relationship between approval rating and margin of victory. Whereas if you just look at the confidence interval, all you know is that it is different from 0, but there's no way to quantify how unusual that statistic is. Whereas the hypothesis test allows you to say the probability of getting a test statistic this extreme is basically impossible if the null hypothesis was true. So what we've established is that this coefficient here is significantly different from 0. And if you notice, and this is what GSS will provide as well, it'll provide for you the t-value. Hey, you were right, McKay. So sometimes people call it t-value. So t-value for this coefficient, and it'll also provide the p-value. So GSS does that, but again, if I just sort of threw up all these numbers, you'd be like, what's t-value and how did they get that and what's p-value? And in fact, yeah, this one doesn't call it p-value, they call it, I don't even know, I won't go into interpreting it, but this computer puts it out in this way. I think GSS actually just explicitly says p or p-value or something. So you can check yourself to make sure you're getting an outcome that's more or less close to what's being printed out. So after we've tested for significance and we've established, yes, this variable approval rating is significantly associated with margin of victory, that's just the starting point. That gives us license to move forward to use the model. Yesterday we covered everything up until this point, where we also saw that homework scores, the relationship that it has with exam scores is significantly different from 0. What we're going to do now, after we've established that it's significant, and this is the same for your research projects, you might have some variables that it turns out that they're not significant, and so you end your analysis there. You interpret it, you say it's not significantly different from 0, it contradicts the theory that's out there that says there's a significant relationship, and here's like a reason why I think the theory was wrong, or something like that. But if your variable is significant, then you can use the model to make inferences and to make predictions. And inferences are projecting your sample onto the whole population, and predictions is saying, well, if we had a person like this, or a scenario like this, what is our predicted outcome? So the first will be making inferences. So in this case, it's kind of an interesting inference that we can make because it's a very unique population. So you can only make inferences within the scope of your sample and in the population that it's pulling from. And so the population that it's pulling from is all incumbent US presidents running for re-election. So it's a very, very narrow population. So we can make inferences, but it's only for like a very select group of people. So it's for all incumbent US presidents running for re-election. Their predicted margin of victory is significantly associated with their approval rating. That's the conclusion that we can make, and this is how it's quantified. We can say that the predicted margin of victory can be estimated using this equation. So if we're making this inference, which of the following is a correct interpretation of this regression equation that we've established is significant? So the first one is, for every percentage point increase in the margin of victory, their approval rating increases by 0.84 percentage points. Or, for every percentage point increase in approval rating, the predicted margin of victory increases by 0.84 percentage points. Or the third option would be, for every 0.84 increase in approval, the predicted margin of victory increases by 1. So this is important that you be able to interpret the regression equation, and even when you read through this, you're probably like, they all sound the same, or they all could be right. I have an A, a B, a C, and a huh. Okay, so let's find out. The way to think about it is this is the known value. Your independent variable is not only the known value, but it's the one that's driving the equation. The way that we can understand this is that for each unit increase in our independent variable, so when I say unit increase, it really depends on what the variable is. So if it's income, it's for each $1 increase. Or if it's age, it's for each year increase, whatever the units of your variable is. So in a sense, if approval rating was 1, and we want to know, hey, if the approval rating was 2, a 1 unit increase, this 0.84, originally was 0.84 times 1. Now that you have a 1 unit increase, it's 0.84 times 2. So it's saying each time your independent variable moves up the scale by 1 unit, it's going to cause your predicted margin of victory, or your dependent variable, to move up by 0.84. And so B is the appropriate answer. But I'd say we'll use Chris's example of helping the poor. And I think, what was the relationship between age and the government helping the poor? As you get older, you're less likely to support government intervention. So his equation would be government intervention to help the poor, and some intercept value, some slope value, and then the person's age. And what I could ask Chris, I'd say, Chris, my uncle, is 60 years old. I haven't talked to him about this, and I'm wondering even if I should talk to him. Can you just give me a quick prediction of what his attitudes towards the government helping the poor would be? Do you think you'd be able to compute that if you knew what the intercept was and what the slope was? So in a sense, what you could do is just plug in my uncle's age of 60, and you would get a value for the extent to which the person's attitude about the government helping the poor, and it would be on some scale. And you'd say, hey Brad, I don't think you should bring up this topic with your uncle because my model predicts that he's not going to be very favorable about the government helping the poor. And I'd say, okay, but my brother, he's 22. Can you give me a prediction of what his attitude would be towards helping the poor? And if we know that the relationship is such that as you get younger, your attitude towards helping the poor increases, without even running the numbers, you can say, well, I know he's going to have a better attitude than your uncle because he's almost 40 years younger. And my model suggests that as people get younger, their attitude becomes more favorable. So when I talk about predictions, it's not just predicting future events, but it's making inferences about the population, because your sample is a sample of the US population, and it includes 60-year-olds and it includes 20-year-olds. So that's what you'd be doing. It's very, very helpful if you use what I'll call like illustrative examples. When you're describing the relationship between two variables, it's super confusing for most readers to wade through, like, as x goes up, y goes down, or there's a positive, negative correlation between this variable and that variable. Whereas if you say, for example, my Uncle John is 50 years old, our model would predict that his attitude towards helping the poor is this, whereas my cousin is 20, and you can see his attitude changes. So like, actually put in real people into your model so that you can illustrate what's really going on. Your readers, and I'm your reader, will appreciate that, because then I'll be like, oh, that makes a lot more sense than like just random numbers being thrown around. This is using the model to make inferences about the larger population. And this example isn't the best because our inferences are constrained to only incumbent US presidents. So we don't know many incumbent US presidents running for re-election. We do know one right now, so that's why we bring it up. It's theoretically interesting to know that the relationship between approval rating and margin of victory is significant, but most people are more interested in applying this model to real-world scenarios. And that's sort of what I was saying with Chris's example of like, let's put in real people into this equation. And so in our situation, it's relevant to want to predict Obama's margin of victory or defeat. We've established that there's a relationship between approval rating and margin of victory, but we want to plug in real-world scenarios to make informed decisions or have informed information using our model. So making predictions, it might throw you off because we're doing something very similar and yet it's a different process. So we use the regression equation to predict the value of y for a certain value of x. And so this will involve calculating a point estimate and a confidence interval. We get a point estimate, we know that there's uncertainty surrounding that point estimate, so we need the confidence interval for that point estimate. So the way that we calculate a point estimate is using our regression equation that we've established beta 1 is significant, so that's why we're moving forward. And so specifically our scenario is this. We use the regression equation derived from the observed sample to calculate the point estimate for the predicted value of y at x equals x star. And x star is sort of whatever value we're going to put in. So Obama's current approval rating is 46%. I want you guys to calculate the point estimate for his predicted margin of victory. So for approval, it would be 46 versus 0.46.
There we go.
Because that's how the data was put in, was as percentage numbers. So we have margin of victory ends up being 2.14. So now the key thing to think about here is that this is a point estimate. It's 2.14. The point estimate based off of the sample that we're working with is 2.14. But every time we have a point estimate, which is based off of a sample, we know that there's variation with that point estimate. And so we always need to also look at what's the confidence interval for that point estimate. Even though just 20 minutes ago we were talking about point estimate for beta 1, and we did a confidence interval for that, now that we're using the model to make predictions, we have another point estimate. And because we're always working with a sample, you always have to recognize that there's variation in that sample. So just this point estimate is going to have variation. So that's why we need to then calculate the confidence interval. And really, it's not to see if it's significantly different from 0 or anything, but it's like the example of Chris and my uncle. You know, Chris would say, well, my model suggests that your uncle would have a score of 6 on the helping the poor scale, but you know, it's just an estimate, and I'm 90% confident that he's going to have between an 8 and a 5. or something. There's a range. Like I know he's definitely not going to be a 1 or a 2. My best estimate is 6, 95% confident that it's going to be within 8 and 5. So the point estimate for Obama's predicted margin of victory, given his current approval rating of 46, is 2.14. However, the regression equation used to calculate the point estimate is derived from our observed sample. Thus, it'll vary slightly from sample to sample. As a result, our point estimate, with y equals when x equals x star, also will vary slightly from sample to sample. So we need to calculate a confidence interval for our point estimate. And our point estimate is calculated using the regression equation derived from our observed sample. And the confidence interval takes into account the variation in the regression equation. So in a sense, each time we take a new sample, it's going to create a slightly different distribution. And so it's going to create a slightly different regression equation, just slightly different. It's still going to be more or less significant because we've already tested that, but what the range of values for B1 and B2 are going to vary slightly. So to calculate the confidence interval, we need a way to assess how much the regression equation varies from sample to sample. So just like in the first part of this class, we looked at how the sample mean would vary from sample to sample. If you extend that out to the regression equation, which produces sample statistics, it's going to vary slightly from sample to sample. In both cases, the main thing is that each sample will generate a slightly different point estimate. So that's what we're wanting to see, is how much variation there would be. This goes back to bootstrapping. When we want to find a confidence interval, we do bootstrapping, which basically takes from our original sample, just like we use bootstrapping to generate a sampling distribution of sample statistics. See, this is coming back to haunt you. All these things are from the first half of class, but we use them throughout. We can use bootstrapping to generate a sampling distribution of regression equations to assess how much the regression equation varies from sample to sample. I can appreciate that this becomes confusing. It's easy to see how the sample mean might vary from sample to sample, but also regression equations will behave in the same way. So through bootstrapping, to remind you, we take repeated samples with replacement from the observed sample data to obtain a sampling distribution of regression equations. We're going to do this like 1,000 times, and for each regression equation, so we're going to get a slightly different regression equation each time, we'll calculate a point estimate, which is what y hat would equal when x equals x star, to generate a sampling distribution of point estimates. So it's the same thing that we did with sample means, like we would resample the population and then take the sample mean of that new sample, and then we'd do another sample and take the sample mean. So we do the same thing here. And then to find the 95% confidence interval, we take the middle, in this case 95% of point estimates, to obtain the 95% confidence interval for y hat when x equals x star. So I'll try to show you visually what's actually going on. This is our sample. It's 11 data points. And when we plotted it out, our computer calculated the best fitting line through here. And that's the regression line. And associated with the regression line is an equation, which is negative 36.54 plus 0.84 times x is the equation. So if we do bootstrapping, we're going to take from our sample and resample, and we're going to get a new distribution of points. Through resampling, this is the new distribution of data points, and so then what we see here is a new regression line forms that fits this new set of data points. So it's same sample, but we're sampling with replacement and calculating a new regression line. And then if we did it again, we get a slightly different regression line. And each of these regression lines have an equation associated with it, and you can calculate the point estimate for each of these regression lines. And if we keep doing it, we get another line, and then eventually we do this 1,000 times, and we get 1,000 different lines or equations, And for each of those, we calculate what the point estimate would be with an approval rating of 46. And so it gives us a distribution of plausible point estimates. 46 is our approval rating. So this is the values that we're interested in looking at, how much they vary. The middle 95% of the predicted values gives us the confidence interval for the predicted margin of victory for an incumbent president with an approval rating of 46. And so we see that basically it ranges from a little over 5 to a little below 0. And because it's an election, we are interested in where the 0 line is, but not because of significance or anything like that. And then increasing the sample size would make our confidence interval narrower. So like if we had more data points, just like with mean height, the more data points you have, the variation from sample to sample is going to be much smaller because you have a lot more information. So if there were more incumbent presidents running for re-election, we could have a larger sample. So that was how we do it bootstrapping. The computer would calculate what all these regression lines were in the point estimates, and it would give you a distribution and say, here's the middle 95% of the values. We can also do it using formulas based on the theoretical distributions. The distributions of this sample statistic, I think it's either normal or t, we'll find out. But we can use sample statistics calculated by the software program and the point estimate formula to calculate the 95% confidence interval for our point estimate y hat. This is the output that you would get in GSS or other software. In GSS, if you tell it to, it'll give you the 95% confidence interval values for the slope. And so for approval rating, the lower bound value of the slope for approval rating is 0.73 and the upper bound is 0.94. And so if you notice, the estimate for approval rating falls right in the center there. And that's what we would expect because it's our best estimate, and then the values are going to range between 0.73 and 0.94. And so then to calculate y hat, we want to know the lower bound. So the lower bound for our predicted margin of victory is going to be beta hat naught lower bound plus the beta hat 1 lower bound for our approval rating. And if you calculate it out, we see that the lower bound is negative 2.89. So it's basically taking the 95% confidence interval values for your betas to calculate what the upper and lower bound of your confidence interval for your point estimate would be. And you would do the same thing with the upper bound. What it gives us then is that the 95% confidence interval for when y hat equals 46% is negative 2.89 to 6.8. So our point estimate was 2.14. But then if you were a betting person on whether or not Obama was going to win based on this model, you would say, based on this confidence interval, it's hard to say. The margin of victory could be negative 2.89, meaning that he loses. So even though our point estimate was 2.14, he's not a shoo-in to win the re-election based on this model. The way we interpret this confidence interval is that we are 95% confident that the average margin of victory for all incumbent U.S. presidents with an approval rating of 46% is between negative 2.89 and 6.8. In a sense, what I just did here was my scenario with Chris of saying, I have an uncle who's 60 years old, and I want to know what's his attitude towards helping the poor. And Chris would say, he would run the numbers and he'd say, okay, here's the point estimate for a 60-year-old person. And this is where the book makes a differentiation, is that what Chris gave me an answer for was for the average 60-year-old. If I wanted to know for a specific person what the range of predicted values is, that's when you do what's called the predicted interval. And we're not going to get into that because it's a whole nother level of complexity. But it's important to know that when you get a value, you're saying for the average person that has this value on the independent variable. And that's all that we have for today.